For our afternoon session. Thanks for getting back on time. And it's a pleasure to have David Ginsbourger here. He's going to talk to us about kernels for deterministic and stochastic approximation of invariant functions. So part of it will be on the blackboard.
Thank you very much. Thank you all for coming, and also for the invitation to the program organizers, the workshop organizers. It's really an uplifting experience to be here among you. And it's a bit it's completely humbling to give a talk after the talks during the whole week and during the morning. So here I will try to present some ideas that come at the same time from the world of deterministic and from stochastic approximations, but that all rely on kernels. And especially I would like to present some ideas pertaining to the use of surrogates and how you can incorporate some prior information in both setups when you do surrogate modeling using kernel methods. So the setup I will focus on during the whole talk is when you have a function f and you're interested in a function f that goes from some domain D to, say, R. Okay? So we could generalize a number of things here to multivariate or more general settings, but for the sake of simplicity, because most of the results I will present here will be dealing with the real valued output case, I will concentrate on that. What I would like to say is that the set D, the input space here, will be assumed Euclidean most of the time, but most of what will be presented can be applied in very general settings in terms of the set D. And the typical situation that we will consider is when you have observations, you have data. Okay? So you have data, and the data, we call it Zi, and Zi is f of xi, or f of xi plus epsilon I. Okay, so there might be some noise here in the observations, where I ranges from 1 to n, and n is an integer, and xi's are points in D. Okay, so the typical setup that we will consider throughout the whole talk, be it in deterministic or in stochastic setups, will be when you would like to say something to reconstruct, to predict the function f based on these observations. Okay? And here again, I focus on pointwise evaluations, but most of what I will present extends naturally to the case where you have linear forms in the function f, arbitrary linear forms. But here let's take this kind of classical pointwise evaluation approximation framework. So when I say kernel, I mean that we will rely on a function k, and k will be a function that goes from D times D to R. Okay? And we will assume that k is symmetric positive definite. Okay? And basically, symmetric positive definite kernels in the real valued case are basically the basis object upon which we can create Gaussian processes, Gaussian process surrogates, and it's also the basic object that underlies the theory of reproducing kernel Hilbert spaces. So when you have this situation here, you can treat that in several settings. You could say my function f is deterministic, and I'm going to try to find a function that approximates f in such a way that it reproduces the observations, or that it fits well with the observations in a way while minimizing some semi-norm, some measure of smoothness. Or I can say in a stochastic paradigm, f is a priori realization of some random process, or some random field, and I'm going to condition my random field on these observations, and then I will have a posterior distribution. So something that I would like to say about that is, okay, stochastic framework, and stochastic framework will be the kind of main framework I will focus on, even if there will be some bridges to deterministic frameworks. Stochastic framework, we will assume that a priori f is represented by a random field. A random field that will be most of the times a Gaussian random field, but some of the results that we will discuss do not necessitate the Gaussian assumption. So a priori, f is represented by z. So zx means that I have a set of random variables that are indexed by the same source space as my function f. And this guy here is characterized, well, by the finite dimensional distributions, which in the Gaussian case are completely characterized by the mean and the kernel function, covariance kernel. So then from there, you can do, you can take surrogates like what we call mn of x throughout the talk. That would be the conditional expectation of zx knowing the observations. Okay, so assume that we are in the case where we have no noise, then we can take the conditioning on zx1 is equal to z1 until zxn is equal to zn. Okay, and it turns out that if you're in a Gaussian case, so under the Gaussian process assumption, and here I'm referring to the talk of Aritha Tekentrup earlier today, you have an analytical formula. Okay, so assume that we take a zero mean Gaussian process. You can write this expectation as k of xn. So here xn is my design. xn has one line and n columns times the covariance matrix k that we will denote by k of xn minus 1. So this guy is assumed invertible. Okay. Times the observations. Okay, so this, let's, sorry, this felt my fault. Let's keep in mind throughout the talk that under such assumptions, we have an analytical formula that gives us a kind of canonical surrogate for the function of interest that relies on a kernel k. And what you can see from the formula is basically that everything is relying deeply on the evaluation of the kernel k at the design points and at the prediction. Okay, so this is what we need to remember. Basically, the kernel k is responsible for the shape of this surrogate, which turns out to be an interpolator in the noiseless case. Now, something very neat about this predictor here. Okay, again, it's mn. Very important note is that mn actually coincides. Mn dot is actually solution to a deterministic problem, which is minimize for all functions in a Hilbert space associated with the kernel k, the reproducing kernel Hilbert space associated with k. There are some appendices in the slideshow if you want to refresh about that. So I'm minimizing the norm of G, put a square or not, it doesn't make any difference, subject to the constraints that G of xi is equal to zi for I ranging from 1 to n. So you can show by a theorem that is called the Kimmel-Dorf-Wabar representer theorem that dates back to 1971, that this mean Gaussian process predictor is also the solution to a deterministic problem. And actually, you can even generalize this. the solution, assuming that you have the matrix is invertible and so on, to the minimization of the OKHS of the sum of squares zi minus fxi. So here we will assume that there is noise, and we will take the sum of squares of the noisy observations minus the candidate function at the point xi, and we will normalize this by some tau I squared. So here I will introduce some regularization that depends on the point, plus the norm of G in the OKHS squared. So as a solution, so the solution to this problem is did I give it a name? Say J star of x is my same vector as earlier times the matrix k of xn plus diagonal matrix with coefficients tau I squared. You don't see that? So let me finish that, and I will just make a comment on that, times the observations, so the vector of observations. So what I just said is that this guy here, which is the conditional expectation in the noiseless case, is the solution to an interpolation problem in OKHS. And then I wrote a regularization problem where we look at the penalized misfit, where the misfit is as weights, which are given. And then I just show here, I'm sorry for that, I did not realize that the solution to this regularization problem is basically the same as this guy, but where instead of having this matrix here, you have this matrix here plus the diagonal matrix of the noise variances. Okay, so there is a nice correspondence between deterministic and stochastic approximation. A big difference, however, is that in the case of Gaussian process modeling, you can enjoy the conditional distribution of the process, meaning you have conditional expectation, but you have also conditional variance, conditional covariance, and you can take samples from the conditional distribution. So let me just briefly illustrate that. So this is the general introduction, definition of a complex valued PD kernel, and then just what we just said on the blackboard, the equations. And now I'm just illustrating that if you take a deterministic function and you assume that, so this is a very classical test case, especially in optimization, you assume that you know this function at 9 points, and now you want to use these tools to surrogate the function. So basically, if you take 9 red points and you look at the conditional expectation, which is also the interpolator in the reproducing kernel Hilbert space, you end up with one function, and then the GP interpretation gives you, on top of that, a pointwise prediction variance, okay, which is something I can write on the blackboard whenever we discuss about it. That gives you a degree of confidence that you have in your interpolation. But more than that, and this is something that maybe some of you do not know yet, you have also the possibility to sample from the posterior distribution and to get basically a measure, a probability measure of a function space that honors your data and your prior. Okay. So these are draws from the posterior Gaussian process that Aritha was mentioning this morning. You have a GP that you assume a priori, then you have your data, and then you have a new distribution, which is the posterior distribution, and you can sample from it. Okay, and then of course you can plug that in any procedure you're interested in nonlinear functional that you're interested, and that gives you some Monte Carlo estimator. Okay? Of course, if you're more clever than that, you can probably do better than Monte Carlo, as many stochastic Galerkin and collocation talks have illustrated throughout the weeks here. So now, what is the real subject of the talk? The real subject of the talk is the incorporation of invariances in these models. So this applies to RKHS, deterministic regularization and interpolation, and this applies to GP, and I will focus mostly on GP because this is the framework where the results were developed, and it also has some additional component, which is the random component that makes it also quite exciting. So the kind of questions that I will try to address in the following slides, so these are some references. The book of Van Lant, I was not sure if it's 2005 or 4. I saw this morning it was 4. But, so the correspondence between reproducing kernel Hilbert space and GP approaches dates back at least to the paper by Kimmeldorf and Waba in '71. It's a fantastic paper. There is also this very nice recent paper by Scheurer, Schabak, and Schlatter about interpolation of spatial data. Is it a deterministic or a stochastic problem? And here is the representer theorem that has been generalized by Scholkopf and co-authors. I will not comment on that right now. So I will just present this slide, which is the opening slide of the section that presents contributions, and the contributions concern the incorporation of prior knowledge in kernel methods for function approximation and surrogate modeling. So basically, if you assume that you have a mean zero or something simple like a constant mean, and you're in one of these setups, everything that you are assuming about f is carried by k. Okay? K is, as you see in the equations, it's everywhere. Okay? It's completely driving the approximation. So basically, if you want to pass a message to the surrogate, you need to do it through k, but k has to be positive definite, and the constraint of positive definiteness makes it somehow difficult sometimes to find kernels that incorporate the prior information you have while remaining valid covariances. So if you think of invariance and k, and if you look at the textbooks about positive definite kernels and covariance modeling, invariance notions are present under the form of so-called stationarity and isotropy. Okay, there is a controller somewhere. Yeah. So probably most of you have come across the term of stationarity. That basically means that your kernel is invariant with respect to translations. So if you translate simultaneously the 2 points, then your covariance is unaffected. And is it maybe the connection is
moving the podium, I think. Podium is not stationary invariant.
So let me benefit from that moment to clean up a bit. So basically my message here is you have stationarity that is a kind of invariance in the sense that if you shift the argument, the left and the right argument simultaneously in the kernel, you have the same value for the covariance. And then you have isotropy. Isotropy is something related to rigid motions, and it tells you that if you rotate or apply any rigid motion to both arguments of your covariance, then it's unaffected as well. But what we are going to say, to present today, is not about isotropy or stationarity. It's about something that is stronger than that. It's about properties that you would like all the functions, all the solutions to your problems to honor pathwise. So I would like my RKHS approximator G star if you want, to be invariant under a given group of transformations, for instance, or I would like my random field to be almost surely producing realization that are invariant under some operator. Okay, so this is the topic. We are investigating functional properties that are driven by K. Okay. So the talk will rely to a large extent on a paper which we published, was published 2 years ago with Olivier and Nicolas. And some topics that will appear throughout the talk are based on former references or on other papers that I will cite upon appearance. So the kind of leading example will be group actions, because I know that Henry loves group actions. So do I. So imagine, for instance, that you have a phenomenon, that you have a group, finite group, say. Okay. You have a finite group G. And then you have your function f, and you have a group action. Okay? So a group action will take a point, and you will act on the point via an element of G. So basically, you can think of a transformation in Euclidean space, so like a finite group of rotations or something like this. So here we will look at symmetries in particular. And now you're interested in finding a function, well, you're interested in reconstructing the function f under the assumption that f of g dot x is equal to f of x for all x in the domain and for all g in the group. Okay? So you would like to find a function f that at the same time honors your observations and honors this condition, this hard condition. Okay, hard-coded, you want to have invariance. So we will do it in the case of random fields. So here I'm a bit too early actually on the slides. I didn't want to display that right now, but I can show you in advance. So let's see. So this is a Gaussian process with symmetrical realizations with respect to two axes. Okay, so here you have the first bisector and the second bisector. So basically, I mean, it's something that always amazes me. I was not aware that it was possible, but something we understood over the years. You can find a covariance kernel such that if you generate sample path from the associated Gaussian process, then all of them, probability 1, will have the symmetrical property. Okay? This is not very difficult actually to generate this. Okay? You can either know the whole talk and find the right kernel, or you can do a very simple operations, which is to take a Gaussian process and to sum it over the orbits of the group action, and then you will obtain something that will be almost surely symmetrical. Actually, the two are equivalent in a way. So I'm going to show you now something that is related to this example. So imagine you want this to hold, and you take a random field Z. Okay, so take a second order random field Z. And so any random field measurable random field which has an expectation and a variance. Okay? And then I'm going to give you a sketch of proof here, a very, very fast sketch of proof to show you that the property is relatively simple and elegant, that we can control the symmetries of the random field by playing on the kernel. Okay? So assume it has a kernel K, expectation 0. Okay. Expectation 0, and covariance of Zx, Zx prime is equal to K of Xx prime. So now property, well, it's an informal property. The probability, so for all x in D, the probability of Zx is equal to Zg dot x for all g in the group is equivalent to the fact that well, let's put it that way. Let's put the property like that. For all x x prime in D, for all g, g prime in G, the covariance of g dot x g prime dot x prime is equal to the covariance of x prime. So here I'm looking at a property that is a lot stronger than the one I mentioned with stationarity and isotropy. I'm saying that if I affect by a group element the left argument of my covariance and by another element of the group the right argument of my covariance, then the covariance remains unchanged. So in particular, if G is equal to G prime, I recover the old notions of invariance, but here I have something stronger that we can call argument-wise invariance. Okay? So proving that this implies that is relatively straightforward, because if you look at the covariance of G dot x and G prime dot x prime, and you assume that these processes are equivalent, then you can replace the one by the other in the covariances, and you get this equation. You can develop the equation. It's easy. What is a little bit more surprising is that this implies that, and basically it's really a sketch of proof, but the main argument of the proof is the following. It's very simple. Is that if you assume this, then if you take the variance of zx minus zg dot x, well, you can develop it as k of x minus twice k of g dot x plus k of g dot x. And then, since you know that the left invariance and the right invariance occur, it's going to be 0, and you have a process, you have a random variable which has a variance 0 and an expectation 0, so it's 0 with probability 1. So is the reason why when I simulate from that guy I got something which is symmetrical, but what is really way stronger and more surprising is what happens next. So imagine that we take one of these realizations and we say this is the function that we want to surrogate. I have a function that is symmetrical with respect to a group of symmetries, and I know the function at some points. Here they have been generated randomly. It's a very poor idea. It's just uniform design, just for the example. And I will now look at the posterior distribution of Gaussian of the true generating Gaussian process, knowing the yellow observations. Okay, so here is my conditional expectation. This is the true function. This is the conditional expectation. See that here with this small number of points, I have almost perfectly reconstructed the function. Of course, I know a lot. I know the points, and I know a four-element group that leaves my function invariant. So basically, 4, 6, 8, 10, 11, 15 points. It's almost as if I had 60 points. Okay, but we don't need to replicate them. And it's even stronger than saying that we replicate the observations, because here we account for this regularity that a symmetrical function is supposed to be near the axis of symmetries, for instance. But the thing that is really exciting, at least to me, is that you have a prediction variance that is also symmetrical, and you have a conditional process. So then you can generate a family of functions that are interpolating your points and that are all symmetrical, which is at the same time a good news and a bad news, because it means that you have a fantastic stochastic surrogate that incorporates everything you wanted to incorporate. The bad news is that if you made the wrong choice at the beginning, you're doomed, because it's going to be symmetrical forever. Okay? So it's important. Okay, so now we will generalize these results. So first, let us take a step back and think about this proof here. So let me remove this for a moment and reformulate this invariance in a way so that we see things a bit clearer. So we have assumed that the function is invariant by the group action, and actually, you remember I told you when we simulated the invariant Gaussian process, I told you that we could have basically taken the sum over the orbits. So basically we can take a random field or a function. Well, let's take a function. So we can take a function and we can sum it over the orbits. We can take the average of a symmetrical function, of a non-symmetrical or a symmetrical function, and then divide by the order of the group. Okay? So we can take that. And basically, if you think hard about it, or if you know group theory already, then being invariant precisely means that T of f is equal to 0, where T of f of x, so T of f is an operator that transforms f at any point x into f of x minus this average over the orbits. So basically, what we have imposed by playing on argument-wise invariant kernels is that the function f must be in the null space of a certain linear operator that subtracts the average over the orbit of a function. But basically, it was maybe not clear from the proof, but it appears from the attempt to generalize this result to several other invariances. The mechanism that come into play in the proof actually generalizes to many other linear operators. Basically, if you have a linear operator that is like this or of a more general fashion, assuming it's compatible with the structure of the GP or of the reproducing kernel Hilbert space, then if you have a kernel that is invariant, left invariant and right invariant with respect to this operator, then the surrogate will be invariant as well. So, about invariances, group invariances, of course it's a topic that is really hot in machine learning. There was already some previous work mostly in classifications, okay, pattern analysis. We have published a paper in 2012 about using that inside of Gaussian process models. A few properties in reproducing kernel Hilbert space, basically that it's argument-wise invariant if and only if the eigenfunctions of the covariance operators are invariant themselves. And then there are some recent papers. I think it's coming back in fashion because people tried looking at some really exciting applications where they need invariances. Okay? So in particular, there are some 2015 papers at NIPS on the topic. So now here is the result of the attempt to generalize this operator to a larger class of operator. I didn't insist too much, but the result I presented on the blackboard doesn't require Gaussianity. It's for any random field that possesses a covariance. Okay? And so is this one. So if you take a measurable random field, which has trajectories or paths that are almost surely in some function space, f, and then you take a linear operator from f to itself, which can be written in the form T of g of x is equal to the integral of g with respect to a measure, a signed measure that is indexed by x, and assuming some technical conditions for a Fubini theorem to apply, then you have the equivalence between invariance up to a modification and the fact that the mean and the kernel of the random field are in the null space of the operator T. And if you assume furthermore that is a technical assumption that the image process is separable, then you can put the x inside of the probability and you have that pathwise you have almost sure invariance of the random field realizations. So then you can play with that, and you can try to find operators of that form that incorporate prior information that you would like to incorporate in your model, if possible. So one example that was developed in the PhD thesis of Nicolas Durand. So Nicolas Durand defended in 2011 and worked, among others, about additive modeling. And basically, we wanted to do some connection between GP and additive models. Okay? Additive models is a very useful setup for high-dimensional modeling and surrogate modeling. And GP is the main research topic we were working on, and we try to incorporate the additivity assumption inside of GP. So can you incorporate that assumption? Yes, you can. So one thing you can do is to simply take sum of univariate kernels. So we showed that if you take a kernel of that form, then the trajectories that are generated by the GP are additive. And then we later on characterized, so it's not only the only form that leads to additive GPs. So here is an example of the functions that you can generate. So this is from Nicolas. These are additive functions that are realizations of Gaussian processes with kernels of that form. And in this paper here, we have given a characterization of kernels that leads to additive realizations, almost surely. So now, let's investigate some generalization, or maybe some more precise statement that we can make in the Gaussian case, because so far we have not assumed Gaussianity. But if it's Gaussian, then we know a lot more. So if it's Gaussian, then there is a powerful isometry called the low-F isometry that tells us, here you have to believe me if you don't know the notions, because we don't have time to introduce everything, that there is an isometry between the Hilbert space generated by the Gaussian process, okay, which is the closure of linear combinations of the field at pointwise at points, and the reproducing kernel Hilbert space associated with the covariance kernel. And if you use that, then you can show for a linear operator such that T of the field at a given x, at any given x, is an element of the Hilbert space generated by the process, that there exists an operator curly T, which is not defined on the path space, but which is defined on the RKHS, such that you can take this T out of the covariance and it becomes a curly T. So the covariance between T of Z and Zx prime is equal to curly T of the kernel applied at the point X. And such that you have this limiting property, so this continuity property basically. And then you can show that you have T of Zx is equal to 0 almost surely, if and only if this curly T operator applied to the kernel is equal to 0, which means that the RKHS is inside of the null space of this operator. Okay, so basically it means that the operator is 0. So some examples. Let's come back to some practical examples. So one example that applies to Gaussian and to non-Gaussian is as follows. We spoke about...
I don't get lost. I want to understand what you just said. So what you're telling me here is how I should construct my kernels if I can build this operator T that embeds the symmetries I want. You just told me that it's kind of homogeneous or linear on that thing, and I apply that thing to the kernel instead of to the realization.
No, it's giving you a condition on the kernel such that it occurs. It's not something you should do. It's something that you should ensure. Then the way to go from an arbitrary kernel to an invariant kernel is not yet touched upon. But here we are exactly doing that. So thank you for helping me with the transition. So imagine that now you're interested in a field or in a GP which has...
Can I ask a quick one just related with the previous
Yes.
thing that you said? You said that in the separable case where the function is a sum of functions of one variable at a time,
Univariate? Yep.
yes, you could find the kernels. Just curiosity, if you're given, say, an ANOVA structure, can you do that as well?
Exactly the same. Yeah, it's the end of the talk. But just a few references, because we don't have time to cover everything, but it works the same. So, but at that time we did not, at that time we thought about generalized additive models. That was the focus. And later on we realized that it was applicable to ANOVA. So imagine that you're interested in a GP or in a function, in a surrogate model, which integrates to zero. So this is centered, but not in the sense of expectation zero, but in the sense of pathwise integral zero. And I remember I was presenting this at a summer school, and someone asked from the audience asked, why can you use that for? And then someone else from the audience said, well, I have some chemical engineering applications where I would like to incorporate that. Okay, so that it could be the case for some reason that you have the prior knowledge that your function integrates to zero. But then what you can do, for instance, so a constructive way of incorporating the invariance is just to take the kernel that corresponds to the centering operation. Okay, so I'm taking a random field z, I'm doing z minus its integral, and then I'm calculating the kernel, and I get this. This is a kernel which path almost surely will be centered. Another one which is more exciting is this one that comes from a paper by Shabak and co-authors that is argument-wise harmonic. So this kernel here has the property that if you take the Laplace operator with respect to one argument, it's equal to zero. So then if you take that guy and plug it in OKHS or your favorite GP, your realizations will be harmonic as well, and interpolating your data. So we can generate sample paths that are pathwise, that are of integral zero. We can also generate a Gaussian random field that is harmonic. And now I will just show this result that is a little bit heavy. Took some time as well to write up by going through the literature on Gaussian measures on Banach space. Basically what the result is telling you is that if you have a prior, if you think of the GP as a prior measure on function space, that is a Gaussian measure, and if you look at the posterior measure, and if you assume that your covariance operator is left invariant by the operator T, then this will be carried over to the posterior measure, so that basically there will be there exists a disintegration of the measure such that whatever the conditioning, you still have invariances of your posterior distribution. So let's use that. So we come back to the pathwise zero integral kernel. So here we take a very simple example that is basically made to make the point that it can be useful, but of course it's made up. Okay, so we have the function here that is red. Okay, we think of the f as the red function, and we know the red function at the crosses, and now we are taking a basic surrogate, okay, which is now black, and the basic surrogate has no clue that there is a bump here that we completely missed. But if you take the kernel that knows in advance that you have integral zero, then it has negative values here and positive values there, so somehow it needs to overshoot the data in order to compensate, so that in the end you have zero integral. So you can do the same with harmonic. So here we have a case where we interpolate an harmonic function based on 4 points. And now I'm going to present two numerical applications that are in the same vein as the previous ones, and then we can conclude. So the first application is, well, is an artificial test case where we assume harmonicity. So for some reason we imagine this setup, okay? So imagine that you have an oven, that the oven is really hot, and that you want to infer the temperature in the oven. You have an oven in form of a disk for some reason. And you can put a few sensors inside of the disk, and here towards the door, but not in the back. Well, it's a completely metaphoric explanation for the design. But imagine that you know the temperature here at the boundary, and you know the temperature in the middle, and you want to infer the temperature on the boundary here. Okay? And in particular, what you want to infer is the maximum temperature in this region. So basically, on the left, we consider a Gaussian kernel, and on the right, we consider a biharmonic kernel, and the realization has been generated in so as to be harmonic. So if you look at the prediction error, well, it's a bit unfair because, of course, the function is harmonic, so you do better with a kernel that incorporates the harmonicity. Okay, do much better actually than with a Gaussian kernel. But what is more interesting is if you look at the reconstruction of the temperature profile at the bottom, then you have something that is almost perfect with the biharmonic kernel, where you have uncertainty that remains with the Gaussian kernel. And if you look at the maximum temperature, well, you can do conditional simulations of the field, and you can look at the maximum conditional on the evaluation points under the different kernels that we are looking at. And here you can empirically, we can recover some kind of Monte Carlo sample from the maximum value of the field under the Gaussian assumption and under the biharmonic assumption. And here you see that it fits well with reality, which is basically this black dashed line. Okay, now the second example is somehow, it's a very simplistic example, but I think it's really where I want to go next.
So in some way, intuitively, what that this shows is the amount of information that this constraint actually provides, right?
Yes.
Yeah.
This is what is really
Exactly.
There
Exactly.
is a linear constraint there of being harmonic, and this is what it yields.
Yes, exactly. So the next example is something that we have unfortunately not yet developed as much as we should have, I guess, but it's something coming. It's ongoing work. So this is in the published paper, but I think deserves some more research. Is the idea to use this theory to estimate invariances. Okay, so imagine that you have the situation where you are in the dark, you have a function f, you have a few observations, and you want noisy observations, and you want to infer, is this symmetrical, is this additive, is this zero integral, yes or no? So here we address a simpler problem, which is I know it's symmetrical, but I don't know the axis of symmetry. So basically, we are going to take this function here with noisy observations, and then we are going to assume that it has a invariant kernel driven by an axis that is parameterized by two parameters. So, well, basically two parameters. And then we are going to do maximum likelihood on the two parameters that parameterize the axis. So basically, we try to understand what is the axis of symmetry of a symmetrical function based on a scarce subset of noisy evaluations. I'm not sure that there are so many methods that can do that, actually. And here is what you get. So this is the contour line or the heat map of the likelihood, the log likelihood. And what you see is that with these few points, we could almost perfectly recover the actual value of the parameters that parameterize the axis. Okay. Now, from a theoretical point of view, it's based on maximum likelihood, and maximum likelihood for Gaussian process on the compact domain is really hard to get hard results, to get some theoretical guarantees on. Okay, so I cannot guarantee that I'm able to find the axis properly under infield asymptotics. Maybe some more research could enable that, but I don't know. So as a discussion, well, function approximation based on kernels enable us to incorporate degeneracies and invariances. So basically, this is the same story, right? You're in the null space of a linear operator that has some basic properties that ensure that everything exists. That includes symmetries and invariances under group actions. So Henry, if the group is infinite, but you have a Lie group and you're able to integrate and so on, it generalizes. We have not done it, but it's written somewhere in a remark. additivity and further multivariate sparsity, we have a MCQMC 2014 paper where we are investigating that, so we can incorporate the sparse ANOVA decomposition inside of the kernel. And harmonicity, and actually there is a literature, Scheurer and Schlatter have published a 2012 paper where they incorporate divergence-free and rotation-free properties in vector fields. Basically, it's not exactly the same way of discussing things, but in the end, it's exactly the same machinery. So, in the Gaussian setup, we have this, at the same time, very nice and tricky property that the invariance will be inherited forever. So even if your data is telling you, I'm not invariant, then the conditional process will be invariant forever. So it can be a problem, and probably there are some ways to get around this. And as perspectives, I would really like to develop further the idea of inferring degeneracy invariance based on this theory, creating kernels that incorporate a bit of invariance and a bit of non-invariance or ortho-invariance. So basically have kernels that are not as rigid as argument-wise invariant kernels and determine by inference what is the importance of each block. And then, of course, explore the potential of this for applications. So you can imagine in physics, plenty of invariances around, in biology, the molecules, engineering, sometimes you have parts in engineering that are symmetrical with respect to some symmetries. And thank you very much.
Any further questions? Yeah. Go ahead. I'll get you next.
Yeah, I guess. So let's go for the other guy.
Okay, fine. We'll go with you.
I think you started to answer my question, but perhaps not. So I was thinking about problems where you thought, well, maybe I don't know the integral zero, but maybe I know it has to be bounded or between certain bounds, and I guess your uncertain symmetry gave you that. But instead of fixing it at a maximum likelihood, have you played around with having priors over that, and
No.
would that break the condition? You wouldn't have conditional symmetry, but
That's a very good point. That's a very good point.
it's almost a way of getting rid of that.
Yes.
It's a plague.
Yeah, it's a good point. No, we have not done that.
But there is a way, I'm just thinking, there is a way of decomposing images. Imagine you have an image, you have vertical, invariant, horizontal, you have rotation. There is a way of using, I think it's Hilbert Poincaré series, of decomposing an image into a series with the contribution from each invariant, where you get a contribution for each invariance subgroup or whatever. I think maybe that's. And if it's binary, for example, you would do that, but you would do it inside the exponential family. So that's been done, I think, but I can't remember who did it.
So I don't know that theory, but basically the route I was thinking of following is to take the tensor product space to look at the decomposition of kernel in terms of projections in the tensor's product space on the null space of the tensorized operator and on the orthogonal of it. That would be the kind of idea.
So you can
I think
enforce.
some time for the question. Yes.
So if you can enforce like a symmetry that you need, could you kind of transform that symmetry to say that one half had to be, say, twice as high as the other side, right? Is that possible? So you can enforce like a zero mean, or you've got your symmetric reconstructions. Yes.
Yes.
What could you do something like, say, everything on this side has to be twice as high in amplitude as the other side? Yeah? You see what I'm saying? So around your axis of symmetry, you could say that on the right-hand side of it, values need to be twice as high as, say, left-hand side. Because couldn't you just do some sort of transformation to make
Exactly twice as high, or the order of magnitude.
It's an example.
It's not the same problem.
Well,
So if it's
answer one of them then.
if it's no, but if it's about the variance, then you can do that with heteroscedastic GP by having a variance that varies over space and having a model for that. Very easy to do. You don't need this theory. If you think of exactly twice the size, then if you can cast it as being in the null space of a linear operator, it's perfectly fine.
That sort of thing is okay. Have you found that useful for anything, or
I've not yet thought of it.
okay? I wasn't sure if it was a really specific requirements that you were building in.
It looks feasible.
Okay.
But
No, that's good.
talk about it offline. I will give the floor to my
Thank you.
distinguished colleague, Raoul.
Yeah, don't point this way. Okay, let's think one more time.